Hello everyone. Once again, my name is Achuloy Imuramoto and I will be the one to discuss and report about the paleomagnetism, seafloor spreading, and plate tectonics. For the learning competencies, I have found one, explain how seafloor spreads, and for this topic, uh, I will connect these three main topics to the seafloor spreading and how this paleomagnetism, seafloor spreading, and plate tectonics give evidences to the continental drift theory or supports the theory of Alfred Wegener. Our planet is in constant state of motion. However, if we take a look just below our surface, we find things are always moving below our feet as well. We call this plate tectonics, and it's how continents form, reform, or reshaped. But before we get to that, let's dive underground to learn what's our planet look like from the inside out. There are two types of layer. Our Earth is made up of layers and there are two types of it. To learn about in order to understand plate tectonics, there are compositional layers and mechanical layers. In compositional layers, there are three primary layers: the crust, the mantle, and the core. Um, it's important to understand that the compositional layers refer to the materials or element that the Earth is made of. However, if we take it if we take it how the inside inside the Earth behaves, then we can divide even further into a mechanical layers. These are the lithosphere, asthenospheres, mesospheres, the liquid outer core, and the inner outer core. The lithosphere is the outermost layer of the Earth, which contains the entire crust and topmost layer of the mantle. The asthenosphere contains the same material as the top layers of the mantle, but the pressure and the heat is increased, and it's not uh, exactly a liquid, but it does move like a heated rock. So you could say somewhat fluid. Mesosphere, at this level, the the pressure is really starting to build, which restricts the molecules, the ability to move, thus making it very rigid. The liquid outer core is extremely high temperature, which melts the metal contained in this layer into a liquid form. Uh, think the flow of a lava and you have a better good idea on what's the liquid outer core look like. And the last one is the inner core. Just like the liquid outer core, the solid inner core has extremely high temperature, which composed mostly of metals, which might lead you to ask why isn't it liquid as well. The answer is pressure. There is so much pressure at this depth that even though the temperature is beyond the melting point of the metal contained in the inner core, the high pressure essentially squishes everything down into a solid. That is why the inner core is solid. Plate tectonics is a theory states that the Earth's outer mechanical layer, the lithosphere, is divided into a large continental-sized plates that are constantly moving. So as you can see on the image, so they are identified plates around the world. We have Eurasian plate, Indo-Australian plate, African plate, and so on. And every year, the plates are moving into 1 to 2 inches per year. And how does this being supported? Scientists discovered dikes over the ocean floor where magma came out and continued to flow. So the Earth is reforming and reshaping. The other evidences is fossils were the same to the other continents. So it's just like the same with the evidences of Alfred Wegener on his continental drift theory. And these plate tectonics serve as one of the uh, supports or evidences that will prove the continental drift theory of Alfred Wegener. So, uh, according to the plate tectonic theory, these massive lithospheric plates were all moving in different ways, and how they interact with one another can have a huge impact on the Earth. So we will identify what are these different types of plate movement. Where these plates meet are called boundaries. And you have three types of plate tectonic boundaries. We have convergent boundaries, transform boundaries, and divergent boundaries. Before I will proceed to convergent boundaries, I want you to remind that the top layer of the plate is the crust, and crust is composed of oceanic crust, which is under the ocean, and the continental crust. Oceanic crust is thinner and denser compared to the continental crust. Convergent boundaries occur when two plates are moving towards another. The results differ depending upon the what type of plates are involved. So we have the oceanic plate and continental plate. Uh, during in oceanic and continental plate, when a thin, dense oceanic plate collides with a relatively light, thick continental plate, the oceanic plate is forced under the continental plate, and this phenomenon is called the subduction zone. The other one is the when two oceanic plates converge. When two oceanic plates collide, one may be pushed under the other, and magma from the mantle rises, forming volcanoes in the vicinity. And the last one is when two continental plates collide, ranges are created as the colliding crust is compressed and pushed upwards. So those are the three types of convergent boundaries. Again, convergent boundaries, volcanoes and mountains form as a result of this kind of uh, plate movement or plate boundary. Just like the Mount Everest, which is a form of a convergent boundaries where two continental plates collides or converge to one another. The second is transform boundaries. Occur when two plates are sliding past to each other in opposite direction, which creates a crack or fault on Earth's crust. As the plate moves, they rub against one another, resulting in building up of pressure. If the plates are stuck on a long period of time, the pressure will continue to build fault line, until eventually it releases, resulting in an earthquake. The largest transform boundaries in the world is the San Andreas Fault. The last one is divergent boundaries. Occur when two plates are moving away from one another. Either the space between two plates widens and becomes a large crack or rift, such as the East African Great Rift Valley that runs on the Lebanon to Mozambique, or the space between the plates under the ocean, where crust is thinner and magma oozes up from the Earth's mantle and fills the space. And this is what we call the seafloor spreading. Example of a divergent boundaries is the Lake Thingvalavatan. It was formed by the Thingvellir Reef, where the North American and Eurasian tectonic plates are tearing or rifting apart over a hotspot on the island of Iceland. We have learned that the seafloor spreading is a formation out of a two-plate movement that move apart from each other, or the divergent boundaries. Seafloor spreading is a hypothesis that was thought of during early 1960s that suggested that the new seafloor is created where two plates move away from each other at mid-ocean ridges and molten basalt rises from within the earth to form new seafloor. It was Harry Hess advanced the theory of seafloor spreading. Hess proposed that the seafloor separates at mid-ocean ridges where new crust forms by upwelling magma. The newly formed oceanic crust moves laterally away from the ridge with the motion like that of a conveyor belt. Old oceanic crust are dragged down at the trenches and reincorporated back into the mantle. Oceanic crust ages, or the more distant it is from the mid-ocean ridge, the old it is. Now, to equal out all the new oceanic floor that is made, there are places called asubduction zones. It is typically a long, narrow areas where one tectonic plate sinks under another tectonic plate, or where uh, oceanic crust is subside or being sink to a continental crust and is then formed into a magma. Typically, when this happens, is the denser plate of the two slides underneath the less dense plate. From this, we can summarize that the seafloor spreading is a formation of new crust, and subduction zone is the destroying of old crust. So this process helps keep the Earth in its fairly shape. And one example of it, or best example, is the Mid-Atlantic Ridge. Now, we are on the last main topic, which is the paleomagnetism. So it is the residual magnetism in ancient rocks, showing direction and intensity of Earth's magnetic field at the time of the rock's formation. So although Alfred Wegener would not live to see it a history of continental drift, uh, uh, um, this would gradually gain acceptance within the scientific community as more evidence uh, accumulate. So Earth's magnetic field is defined by north and south that aligns generally within the axis of rotation. The lines of the magnetic field or magnetic force flows into the Earth in the northern hemisphere. As you can see, the arrow is upward, and out in the southern hemisphere. Out, in, out, in. At the north, and south poles, the force is vertical. As you can see, the red arrows there. Anywhere on the equator, the force is horizontal. And everywhere in between, the magnetic force is at some intermediate angle to the surface. So as you can see on the image, depiction of the Earth's magnetic field, as a bar magnet coinciding within the core. It is the core that uh, uh, it is the core that contains or that releases magnetic field for us to protect from a solar winds. So the red arrow there represents the orientation of the magnetic field at various locations on Earth's surface. On the second image is the during the seafloor spreading, wherein there is an upwelling of magma. And this upwelling of magma will cool down and result to a basalt or uh, rocks that contains an iron or magnet, uh, uh, magnet kind of material. So the normal magnetic polarity is represented with a color 1, while the no color there is represented as the reverse magnetic polarity. So uh, when the uh, magnetic field is reversed, there is a reverse magnetic polarity happen, wherein if it is on its normal polarity, this represents the uh, new crust, or this represents the colored crust being formed. So in a paleomagnetism, there is what we call a polar wandering and apparent polar wandering. So a polar wandering pertains to slow movement of the Earth's magnetic poles relative to a geographic poles. So as you can see there, it is the continent that is fixed, and the pole is wandering or changes its location. While the other one is the what we call the apparent polar wandering, wherein it is the continent that drifts away, or that drifts away or moves apart from each other, and not the uh, magnetic poles. So remember, in our seafloor spreading, so in each fluid form, the minerals that make up magma are free to move in any direction and take on any orientation. But as the magma cools and solidifies, the movement ceases and the mineral orientation and position become fixed. As the mineral magnetite, or the material that comes up from the magma, crystallizes, it becomes magnetized with an orientation parallel to the Earth's magnetic field at that time. Remember the polarity, uh, when when the when the magnetic field is in reverse, there is what we call the reverse polarity, or when the magnetic field is in a normal position, there is a normal polarity, or or magnetic the movement or the point of the magnetic field. So so it becomes magnetized with an orientation parallel to the Earth's magnetic field at the time. So similar to the way a compass needle aligns with the magnetic field to point north direction, or north. So this magnetic record in a rock is what we call a remnant magnetism. So rocks like basalt, which cools from a high temperature and commonly have relatively high levels of magnetites, are particularly susceptible to be magnetized in this way. Uh, but even sediments and sedimentary rocks, as long as they have small amounts of magnetite, will take on remnant magnetism, because the magnet grains gradually becomes oriented uh, following deposition. Mm. By studying both the horizontal and vertical components of the remnant magnetism, one can tell not only the direction to magnetic nor to the direction at the time of the rock's formation, but also the latitude where the rock formed relative to the magnetic field. Remember, there is a vertical, horizontal, or inclined. So there is a group of scientists, geologists, uh, that started looking at the remnant magnetism of the Phanerozoic British and European volcanic rocks and collecting a paleomagnetic data. They found out that the rocks of a different ages sampled from generally the same area showed quite different apparent magnetic pole. So they have different positions or magnetic poles position. So they initially assumed that that this meant that the Earth's magnetic field had over time departed significantly from its present position, which is close to the rotational pole. So as you can see on the image there, on the left side, or what we call the polar wandering curves, the curves from the Asia and North America seem to show that the North Magnetic Pole was located in a two places simultaneously throughout history. However, in the right side, uh, uh, if the continents are rearranged into a Pangea or as one pa siya, the two curves overlap, showing that uh, it is the continents that have moved and not the pole or the magnetic pole. Magnetic poles rather. So the curve defined by the paleomagnetic data was called a polar wandering path. The line there, the green and the red. And these geologists initially thought that their data represented actual movement of the magnetic poles. But, however, we know now that the uh, magnetic data defined movement of the continents and not the uh, magnetic poles. So we call it as the apparent polar wandering, wherein it is the continent that moves and not the magnetic poles. So that's it. Uh, in this really uh, supports or give uh, evidence to the mm, uh, continental drift theory of Alfred Wegener, that it is the continent that drifts away uh, from each other through the movement of the plate tectonics, the seafloor spreading, and the evidences or the evidences of paleomagnetic data that it is really the continent that moves. So the significance of this topic or of this lesson really helps or really supports the theory of continental drift of Alfred Wegener, because that time um, walay mutuo sa iyaha. It is because how come daw the continent moves apart or nagdrift away, na they thought that the fixed daw or constant daw ang continent or ang crust sa ilalom sa dagat or sa seafloor. O how come daw nga mag-move ang katong mga continents. So it is through plate tectonics and the seafloor spreading that will serve as a support to the continental drift theory of Alfred Wegener, as well as this paleomagnetism that uh, really identifies the the location or the exact direction of the rock or of that continent through the magnetic field. So for my reference, here are my references.